Today we will read about ultraviolet absorption spectroscopy. Introduction. One of the most important field of activities of an organic chemist is the determination of structural formula of various substances. In the earlier days, the structure elucidation was mainly based upon the study of classical physical properties, melting point, boiling point, refractive index, and chemical reaction of the compound. The procedure involved was rather laborious and time consuming. However, in the last 50 years or so, some remarkable physical methods have been developed to serve as powerful tools for structure analysis. Of these, the most useful and commonly employed methods are the spectroscopic methods, which are based upon the interaction of electromagnetic radiations with the substance under examination. These methods may further involve the study of UV, infrared, nuclear magnetic resonance, and mass spectra. Mass spectroscopy is employed to determine the molecular mass and molecular formula of substance, while UV and infrared are used to determine the nature of functional group. Finally, the NMR spectroscopy is used to know the complete structure, including the stereochemistry of the substance. The major advantages of employing these spectroscopic methods for structure determination and identification of substances are as follows. They need very little time, and the information obtained is often a permanent record in the form of a chart. The substance is required in very small quantities. The methods are extremely sensitive and highly reliable in establishing the structure of compounds and analysis of mixture of closely related compounds. They can be used for the detection and identification of even very short-lived reaction intermediates. During the spectroscopic studies, the compound is not generally affected chemically and can therefore be recovered unchanged. Continuous analysis is often possible, facilitating the study of reaction rates. In this chapter, we shall deal with some basic concept of UV spectroscopy, the electromagnetic spectrum, and spectroscopic studies. Electromagnetic radiations. Many spectroscopic techniques are based upon the interaction of a compound with light or some other form of electromagnetic radiations. It is well known that light and other electromagnetic radiations are different form of energy which have a dual character. They have the property of both a wave and a particle. They are called electromagnetic radiations because they consist of oscillating electric and magnetic fields which are perpendicular to each other and perpendicular to the direction of motion of radiations. Some important characteristic of these radiations are the energy of these radiations is inversely proportional to their wavelength or directly proportional to their frequency. These radiations do not require any physical medium and can be transmitted through empty space. For example, light reaches us from the sun through empty space. All type of electromagnetic radiations travel through space with the same velocity, which is nearly 3 into 10 to the power 8 meter second inverse. Electromagnetic radiation can be described in terms of characteristics such as wavelength and frequency. Wavelength, it is the distance between two adjacent crests or troughs in a particular wave. It is denoted by symbol lambda. The wavelength is usually expressed in meter, micrometer, nanometer, or angstrom. An older term for micrometer is micron, and older term for nanometer is millimicron. Frequency, it is the number of waves which pass across a point in 1 second. It is denoted by symbol normal. The frequency is generally expressed in cycles per second or simply as inverse or hertz. The frequency and wavelength are related to each other. Normal is equal to c upon lambda. C is the constant velocity of light wave number. It is the reciprocal of wavelength and represents the number of waves per centimeter. It is denoted by the symbol normal bar. Wave number is generally expressed in centimeter inverse. Reciprocal centimeters. Wave number is related to wavelength and frequency as normal bar upon 1 upon lambda is equal to normal upon c, where c is the velocity of radiations. In SI system, the unit of wave number is meter inverse. Energy of electromagnetic radiation. Electromagnetic radiations are associated with this discrete energy units called quanta or photon. The energy of a photon is directly proportional to its frequency or inversely proportional to its wavelength, as shown by the following equation. E is equal to hv is equal to hc upon lambda, where h is Planck's constant 6.625 into 10 to the power minus 34. Electromagnetic spectrum. Visible light which can be detected by the human eye constitutes only a very small part of electromagnetic radiation. The full range of these radiation is indeed very large, and their wavelengths vary from a very small fraction of a meter to many kilometers. The arrangement of entire range of electromagnetic radiation is increasing order of their wavelength or decreasing order of their frequencies is known as electromagnetic spectrum. The complete electromagnetic spectrum, along with common names used to identify different ranges of wavelengths. Principle of absorption spectroscopy. It is interesting to note that practically all the important spectroscopic methods used for structural analysis belong to the field of absorption spectroscopy, which studies the absorption of electromagnetic in relationship to molecular structure. When a beam of electromagnetic radiation is passed through a substance, the radiation may be either absorbed or transmitted depending upon the wavelength of the radiation and molecular structure of the substance. Absorption of radiation would naturally bring about an increase in the energy of the molecule. The energy gain begin being directly proportional to frequency or inversely proportional to wavelength of a radiation. The increase in energy of a molecule may lead to electronic excitation, whereby electrons are raised to higher energy levels. Alternatively, it may bring about an increase in the vibrational or rotational energy of the molecule. A very important condition for a molecule to absorb electromagnetic radiation is that the energy of a photon of the radiation must be equal to the energy difference between two vibrational or rotational or electronic energy states of the molecule. In other words, the particular wavelength of a radiation that a given molecule can absorb is determined by changes in vibrational or rotational or electronic states that are permitted to a molecule of the structure. The absorption of radiation is absorbed instrumentally by passage of radiation through a sample of substance and automatic analysis of the intensity of transmitted radiation. A record of the amount of radiation absorbed or transmitted by a given sample as a function of wavelength of radiation is called absorption spectrum. Having discussed the principle of spectroscopy, we proceed further to discuss ultraviolet spectroscopy in some detail. Ultraviolet spectroscopy involves the measurement of absorption of light in the visible and ultraviolet regions by the substance under investigation. Since the absorption of light involves the transition from one electronic energy level to another within a molecule, UV spectroscopy is also known as electronic spectroscopy. It will be quite appropriate at this stage to study the laws which govern the absorption of light. The absorption laws. There are two laws which express respectively the relationship between absorption of light by a substance and its molar concentration and the length of the path through which the light passes. These are Beer's law. According to this law, when a beam of monochromatic light is passed through a substance dispersed in non-absorbing solvent, the absorption of light is directly proportional to the molar concentration of absorbing substance. Lambert's law. When a beam of monochromatic light is passed through a substance, the absorption of light is directly proportional to the path length of the sample of the substance. Beer-Lambert's law. Two laws stated above can be combined to get a general absorption law termed as Beer-Lambert's law. It may be stated as the absorption of light by a substance at a particular wavelength is proportional to the number of molecules of substance in the path of light. Therefore, Beer-Lambert's law may also be expressed mathematically as A is equal to log I naught upon I is equal to ECL. Limitation of Beer-Lambert's law. Beer-Lambert law is strictly obeyed when dealing with the UV spectra of single species. However, if a sample contains different structural forms of the molecules in equilibrium with each other, such as in case of keto-enol tautomers, the law is not obeyed. It is also not applicable if the solute sample and solvent interact with each other to form a complex smaller absorptivity. It is proportionality constant which relates the absorbance at a particular wavelength to the molar concentration of absorbing substance and the length of the path of light in centimeter. It may be expressed as E is equal to log I naught upon I upon Cl is equal to A upon Cl. Molar absorptivity is a measure of intensity of absorption at a particular wavelength and has the dimension of centimeter scale mole inverse, but these units are seldom used. The transmittance of a sample will be naturally given by the relation T is equal to I upon I naught, Therefore, percent of transmittance is equal to 100 into 1 upon I naught. Mechanics of recording the UV spectrum. Presentation of the spectrum. Excellent ultraviolet spectrophotometer are now available which are conveniently record the spectra over the ranges 200 to 800 nanometer. 200 to 4 nanometer is known as near ultraviolet region, while 400 to 800 nanometer is visible region. Since oxygen of atmosphere strongly absorbs light at about 200 nanometer and below, the use of wavelengths shorter than 200 nanometer is not practicable unless special vacuum techniques are employed. The procedure for recording the ultraviolet spectrum, the given compound is generally dissolved in some suitable solvent which does not itself absorb light in the region under examination. The commonly employed solvent are 95% ethanol, hexane, and water. The solution of compound is placed in a suitable transparent container which does not absorb light in the region being studied. Generally, a quartz cell of 1 centimeter path length is used for this purpose. Glass cannot be used since it absorbs strongly in ultraviolet region. At the same time, some solvent is taken separately in another quartz cell which serves as a reference cell. The sample solution and the solvent are then exposed to ultraviolet and visible radiations in spectrophotometer, in which a hydrogen discharge lamp is usually employed as a source of light in the ultraviolet region, while a tungsten filament lamp is used for visible region. The spectrometer operates by comparing the amount of light in the beam transmitted through the sample with the reference beam which passes through the reference cell. This compensates for any absorption of light by the cell and the solvent. In this way, the spectrometer measures the amount of light absorbed by the compound at each wavelength of the ultraviolet and visible region. This absorption gets recorded on a chart part of as a plot of wavelength of the entire region on horizontal axis versus the absorbance of light at each wavelength on the vertical axis. The spectrum obtained consists of a small number of broad peaks. Quite often, only one peak is seen. UV spectrometer, a simplified diagram of UV visible spectrometer. It consists of following parts: a source of radiation which emits all wavelength of UV radiation. The commonly used source of light in the UV region is the hydrogen deuterium discharge lamp, while a tungsten filament lamp is used for producing visible light. A monochromator which separates the radiation into individual wavelengths. The single wavelength of radiation is split into two beams, one of which passes through the sample cell while the other passes through the reference cell. A detector which continuously measures the intensity ratio of beams transmitted through the sample and the solvent respectively. A recorder chart paper which automatically records the absorption of light at each wavelength as a graph of absorbance versus wavelength. Presentation of spectrum. The ultraviolet spectrum of 1,3-butadiene in hexane. It may be seen that absorption of ultraviolet radiation by 1,3-butadiene begins at wavelength below 200 nanometer and continues up to about 260 nanometer. The absorption is maximum at 200 to 217 nanometer top of the peak. Sometimes the ultraviolet absorption curves are also presented by plotting molar absorptivity against wavelength. For example, the ultraviolet spectrum of acetone in hexane plotted as E versus wavelength. It may be seen that the maximum molar absorptivity is about 15 at lambda max is equal to 279 nanometer. Now we will read about principle of UV spectroscopy. Absorption of visible and ultraviolet light produces changes in the electronic state of molecules associated with the excitation of an electron from a lower to higher energy level, but it must be noted that each electronic level in a molecule is associated with a number of vibrational sublevels, and each vibrational level in turn is associated with a number of rotational sublevels. Therefore, in its transition to higher energy level, the electron can go from any of the sublevels corresponding to various vibrational and rotational state in ground state to any of sublevels in excited state. Appearance of broad bands and not sharp peaks in the spectrum. If the electronic excitation in the molecule had occurred without any accompanying changes in vibrational and rotational sublevels. The spectrum would have consisted of sharp lines, with each line representing a change in electronic state. But due to the mixing of vibrational and rotational changes with the electronic changes in molecule, there will be a large number of possible transitions requiring only slightly different energies. This will require the absorption of a large number of wavelengths which are very close to each other. As a result of the absorption, spectrum contains a large number of lines which are too close together to be distinguished separately and are recorded in the form of broadbands in the spectrum obtained. As stated earlier, the spectrum is described in terms of position of the top of hump, lambda max, and the molar absorptivity Emax. Electronic excitation. Electronic transition involves the promotion of an electron from one orbital to another orbital of higher energy. In a molecule, the electron promoted may be a sigma electron present in a sigma molecular orbital, pi an electron present in a pi molecular orbital, and an electron present in a non-bonding orbital, as illustrated with the help of electron pairs in formaldehyde, as shown on the right hand side. The higher energy orbitals are antibonding molecular orbital, which may be vacant in the ground state of the molecule. The antibonding orbital associated with the sigma bond is called sigma star orbital, and the associated with pi bond is called the pi star orbital. Since the n electrons are not concerned in bond formation, there are no antibonding orbitals associated with them. The electronic transition taking place in ultraviolet and visible regions are of the following type: sigma to sigma star, n to sigma star, n to pi star, pi to pi star. It gives a general idea of relative amounts of energies required for various type of electronic excitations. Transition probability. It is interesting to note that it is not necessary that exposure of a compound to ultraviolet or visible light must always lead to an electronic transition. According transition have been further divided into two types: allowed transition, forbidden transition. Allowed transition, these are transition which have Emax 10 raised to power 4 or more, and the probability of their occurrence is very high. These are generally due to pi to pi star transition. For example, pi to pi star transition in 1,3 butadiene, which shows absorption at 217 nanometer and has Emax 20900, represents an allowed transition. Forbidden transitions, these are transitions for which Emax is generally less than 10 raised to power 4. These are usually related to n to pi star transition. For example, n to pi star transition of a saturated aldehyde or ketone showing weak absorption near 290 nanometer and having Emax less than 100 is a forbidden transition. It should be clearly understood that forbidden transition does not mean that such a transition cannot take place at all. It just tells us that the probability of transition is very low. To clarify this statement, let us consider the n to pi star transition. The orbital containing the non-bonding electrons present on heteroatom lies in a plane perpendicular to the plane of pi star molecular orbital. The regions in space belonging to these orbitals can overlap only to a very small extent. As a result of probability of excitation of an electron to pi star orbitals is very low. Concept of chromophore and exochromes. Chromophore. The term chromophore was originally used to denote a functional group or some other structural feature, the presence of which imparts a color to a compound. For example, nitro group is a chromophore since its presence in a compound impart yellow color to compound, but these days the term chromophore is used in such broader sense. It is now defined as any group which exhibit absorption of electromagnetic radiation in the visible or ultraviolet region. It may or may not impart any color to the compound. Chromophores such as C double bond O, N double bond N, and NO2, which contain both pi and n electrons, they can undergo pi to pi star as well as n to n star transition. Two compounds having the same chromophoric generally exhibit absorption at nearly the same wavelength lambda max and have nearly the same molar absorptivity E max. Therefore, it should be possible to identify the presence of a particular functional group in an unknown compound by the comparison of its UV spectrum with the data of already known compounds. Exochrome. An exochrome is a group which itself does not act as chromophore, but when attached to a chromophore, it shifts the absorption maximum towards longer wavelength, along with an increase in the intensity of absorption. Some commonly known exochromic groups are OH, NH2, OR, NHR, NR2. All exochromes contain one or more non-bonding pair of electrons. Due to conjugation, there is a decrease in energy difference between ground state and excited state of group. As a result, the absorption shifts to longer wavelength. At the same time, there is an increase in the intensity of absorption. For example, when the exochrome NH2 group is attached to benzene ring, it increases delta max, lambda max as well as E max. Change in position and intensity of absorption. For isolated chromophore groups such as C double bond C, C triple bond C, absorption occurs in far ultraviolet region which cannot be easily studied, but the position of absorption maximum and the intensity of absorption can be modified in different ways by some structural changes or change of solvent. These changes can produce four kinds of effects: bathochromic effect or redshift, hyposochromic effect or blue shift, hyperchromic effect, hypochromic effect. Bathochromic shift or red shift. By attachment of oxochrome to the chromophore. When an oxochrome such as OH or NH2 is attached to a chromophore, it leads to conjugation or help in extending conjugation. As a result, absorption shifts to longer wavelength. By conjugation of two or more chromophoric groups, bathochromic shift is also produced if two or more chromophores are present in conjugation in a molecule. By using solvent of lower polarity, it is also possible to achieve bathochromic shift by using solvent of lower polarity. For example, use of solvent of lower polarity produces a red shift in the N2 pi star absorption of carbonyl compounds. Hypochromic shift or blue shift, it involves the shift of absorption maximum towards shorter wavelength. It may be brought about as follows: by removal of conjugation in a system. For example, protonation of aniline causes a blue shift from 280 nanometer to 203 nanometer. This is because anilinium ion thus formed has no lone pair of electron on nitrogen which can conjugate with benzene ring. By using solvent of higher polarity, use of solvent of higher polarity can also bring about hypochromic shift. For example, use of solvent of higher polarity cause a blue shift in the N2 pi star absorption of acetone. Hyperchromic effect. The effect involved in increase in the intensity of absorption. It is usually brought about by introduction of an exochrome. Hypochromic effect, it involves a decrease in the intensity of absorption. It is brought about by group which distort the geometry of the molecule. For example, when a methyl group is introduced in position 2 of biphenyl, hypochromic effect take place due to distortion caused by methyl group. As a result, Emax decreases from 19000 to 10250. It may noted that the bathochromic shift is generally accompanied by hyperchromic effect, while hyper hypersochromic shift is accompanied by hypochromic effect. The various kind of absorption and intensity shift have been summed up in figure 4.7. Solvent effects and choice of solvent. Solvent effects. The solvent used for dissolving a compound under examination has a profound effect on the UV spectrum of compound are given below. Effect on fine structure. As a result of interaction of solute with solvent molecule, the fine structure of absorption bands is blurred out and a smooth curve is obtained. This smoothing out of the spectrum deprives us of much useful information about complex molecule. The smoothing out of effect is more in polar solvent than in non-polar solvents. The fine structure of UV spectrum is best observed in vapor phase. Effect on the position of intensity of absorption maximum. Changing the polarity of the solvent may also lead to changes in position of and intensity of absorption maximum. Effect on non-polar compound. In general, changes in polarity of solvent do not cause any significant shift in the spectra of non-polar compounds such as dienes and conjugated hydrocarbons. For example, the absorption maximum for non-polar compound is practically the same in the alcohol as well as in hexane. Effect on polar compounds. In case of polar compounds such as alpha beta unsaturated carbonyl compound, the absorption maximum generally gets shifted with the change in the polarity of solvent. It has been observed that such shifts are of two types: shift in N to pi transition, increase in the polarity of solvent; shift N to pi transition, pi star transition to shorter wavelength, that is blue shift. For example, absorption maximum of acetone is 279 nanometer in hexane at 270 nanometer in ethanol and 264 nanometer in water. This shift towards the shorter wavelength is mainly due to greater stabilization of ground state than the excited state through dipole-dipole interaction, formation of hydrogen bond or solvation with the polar solvent. As a result, the difference in energy between the ground state and excited state increases and absorption shift towards shorter wavelength. Let us, for example, consider the blue shift of N to pi star carbonyl absorption. The carbonyl group is more polar in ground state than in excited state. Therefore, the extent of hydrogen bonding between ground state and the polar solvent like water and alcohol is much more than between the excited state and the solvent. In other words, ground state is stabilized to a greater extent and undergoes greater lowering of energy than the excited state. Consequently, the energy difference between the two state increases and absorption shift towards the shorter wavelength. Shift in pi to pi star transition. Increase in the polarity of solvent. Shift pi to pi star transition to longer wavelength, that is red shift. For example, it has been observed that as compared to solution in hexane, solution in ethanol generally shows a red shift of about 10 to 20 nanometer. This shift of pi to pi star absorption towards longer wavelength is largely due to greater stabilization of excited state relative to ground state through dipole-dipole interaction or solvation. As a result, the energy difference between the ground state and the excited state decreases and the absorption shift toward larger wavelength. For example, the molecule of ethylene is more polar in excited state than the ground state due to greater polarity of pi star orbital compared to pi orbital. As a result, the pi star molecular orbital will be relatively more stabilized by dipole-dipole interaction with the polar solvent as compared to stabilization of ground state. Therefore, lesser energy will be required for such a transition and the absorption will shift towards larger wavelength. Shift in N to sigma star transition. N to sigma star transition are very sensitive to hydrogen bonding. For example, alcohols and amines form hydrogen bonding with the solvent molecules due to the presence of non-bonding electrons on the heteroatom. As a result, more energy is required for N to sigma star transition in polar solvent and shift toward lower wavelength take place. To sum up, if a group is more polar in ground state than in excited state, increasing the polarity of solvent shift the absorption to the shorter wavelength. If a group is more polar in excited state than in ground state, increasing the polarity of solvent shift the absorption to longer wavelength. Choice of a solvent. A suitable solvent for ultraviolet spectroscopy should meet the following requirements. It should be transparent in the wavelength region under examination, that is, it should not itself absorb radiations in the region being examined. It should be less polar so that it has minimum interaction with the solute molecules and has no effect on fine structure of absorption bands and the position of absorption bands. The most commonly employed solvent is 95% ethanol. It is cheap, has good dissolving power and does not absorb radiations above 210 nanometer. In other words, it is transparent above 210 nanometer. Commercial ethanol should not be used as it contains some benzene which undergoes absorption in the UV range at about 280. Some other solvents which are transparent about 210 nanometer are N-hexane, cyclohexane, methanol, water and ether. Hexane and other hydrocarbon are sometimes preferred to polar solvent because they have minimum interaction with the solute molecules. Benzene, chloroform, and carbon tetrachloride cannot be used because they absorb in the range of about 240 to 280 nanometer. Some characteristics absorption band. The wavelength of maximum absorption and corresponding molar absorptivities or extinction coefficient of some typical ultraviolet band of simple molecule containing different groups. Woodward-Fisher rules for calculating absorption maxima. By studying the ultraviolet absorption spectra of a large number of compounds, Woodward in 1941 deduced certain rules for co-circulating lambda max with molecular structure. Since then, these rules have been modified by Scott and Fisher as a result of more experimental data. The modified rules, known as Woodward-Fisher rules, enable us to calculate the position of lambda max for a given structure by relating the position of lambda max with the position and degree of substitution of chromophore. The calculated value are generally within 2 or 3 nanometer of experimental values. We will now consider these rules briefly for different classes of compound. Woodward-Fisher rule for calculating lambda max in conjugated dienes and trines and polyenes. Before we consider the rule for dienes, trines, it will be useful to explain some terms involved in discussing the rules. Homoannular dienes, it is a cyclic diene which contain conjugated double bonds in the same ring. Heteroannular diene, it is a cyclic diene in which double bond is conjugation are present in different rings. Endocyclic double bond, it is a double bond present in a ring as a ring one endocyclic and one exocyclic double bond. Ring B has endocyclic double bond only. Exocyclic double bond, it is a double bond in which one of the doubly bond atom is a part of ring system. Woodward-Fisher rule for conjugated dienes, trines and polyenes. According to these rules, each type of diene or trine system has a certain fixed value at which absorption takes place. This constitutes the basic value or parent value. The contribution made by various alkyl substituents or ring residues, double bond extending conjugation and a polar group such as Cl, Br, Or are added to basic value to get lambda max for a particular compound. The parent value and contribution of different substituents group. Parent value acyclic conjugated dienes की 217 nanometer, homoannular conjugated dienes की 253 nanometer, heteroannular conjugated dienes 240 nanometer. Increments each alkyl substituent or ring residues 5 nanometer, exocyclic double bond 5 nanometer, each double bond extending conjugation 30 nanometer. Oxochromes. Now we will read about ultraviolet spectra of conjugated enes or enons. It has already been studied that the presence of conjugated system in a molecule plays a very important role in ultraviolet spectroscopy. If a molecule contains two chromophoric groups separated from each other by two or more single bonds, their effect on the UV spectrum of molecule is generally additive. But if the two chromophoric groups are conjugated, they are practically equivalent to a new chromophore and a markedly different spectrum is obtained. To illustrate this statement, we now consider the ultraviolet spectra of conjugated enes and enons. Ultraviolet spectra of conjugated enes. The UV spectra of all enes, whether conjugated or non-conjugated, involve the pi to pi star transition. Still, the spectra of conjugated enes are marked different from non-conjugated enes. This is basically due to the fact that in conjugated enes, the energies of pi to pi star orbitals are much closer together than in simple enes. As a result, the conjugated system require lesser excitation energy as compared to non-conjugated system, and therefore the absorption shift to longer wavelength. All acyclic conjugated dienes exhibit redshift of about 40 nanometer with respect to unconjugated enes, giving intense signal in the region 215 to 230 nanometer. Extended conjugation gives rise to additional redshift along with increase in intensity. Lambda max value of following polyenes clearly illustrated for the effect of conjugation and its extent on the lambda max of conjugated. Ultraviolet spectra of conjugated enones, ketones in which carbonyl group is in conjugation with a carbon-carbon double bond exhibit strong absorption in the region 215 to 250 nanometer due to pi to pi star transition and weak absorption in the 100 310 to 330 nanometer range due to N2 pi star transition as compared to unconjugated ketones. There is a red shift in both the types of absorption due to conjugation. It may be noted that the weak N2 pi star band is sometimes not observed at all because it is marked by the very intense pi to pi star band. The UV spectrum of a conjugated in misty oxide in ethanol is shown in figure 4.12 for the sake of illustration. The spectrum shows pi to pi star absorption band at lambda max is equal to 236. The n to pi star band lambda max is equal to 315 is not observed in the spectrum. Interpretation of ultraviolet spectra. Application of ultraviolet spectroscopy. The interpretation of UV spectra of a known compound can be very useful in deriving structural information about the compounds. The main application of ultraviolet spectroscopy are as follows: detection of conjugation. Ultraviolet spectrum help to show whether a given compound contain certain group in conjugation with each other or not. The conjugation may between two or more carbon-carbon double bond, between carbon-carbon and carbon-oxygen double bond, between double bond and an aromatic ring. UV spectrum can also reveal the presence of an aromatic ring itself and the number of locations of substituents attached to carbon of conjugated system. Since 4-methyl pent 3 2 1 has the carbon-carbon double bond and the carbonyl group in conjugation with each other, both pi to pi star and n2 pi star absorption bands in it will be at longer wavelength than in 4-methyl pent 4 in which there is no conjugation. Thus, UV spectrum enables us to determine whether a compound contain a conjugated system or not. Extent of conjugation. UV spectroscopy is also employed to estimate the extent of conjugation in polyenes. With the increase in the number of double bonds, the absorption shift to longer wavelength. For compounds having 8 or more double bonds, the absorption may shift to even visible region of light. Thus, by determining the lambda max of a given polyene, it may be possible to know the number of double bonds in conjugation. Determination of configuration of geometrical isomers. The above absorption can be justified in terms of steric hindrance in the trans isomers. The bulky group lie on either side of the double bond and there is no steric hindrance. As a result, the ethylic double bond and the pi bond of benzene ring lie in the same plane and the pi orbital overlap of conjugated system is quite effective. Therefore, the trans isomer absorbs at longer wavelength. In the cis isomer, the bulky group lie on the same side of double bond, giving rise to steric hindrance. Therefore, the ethylic double bond and pi bond of benzene are forced to be non-polar. Due to this distortion, the pi orbital overlap is not so effective. Thus, decrease in pi orbital overlap leads to decrease in conjugation. Hence, the cis isomer absorb at shorter wavelength. Detection of functional group. UV spectrum can also be used for detection of certain functional group and other structural feature. If the absorption take place above 200 nanometer, even the absence of any absorption above 200 nanometer is of some utility as it shows the absence of conjugation carbonyl group and benzene rings in the compound. Determination of strength of hydrogen bonding. If a compound form hydrogen bond with protic solvents such as water and alcohol, it is possible to find the strength of hydrogen bonding by comparing the lambda max in the protic solvent with lambda max in a non-polar solvent. For example, carbonyl compound form hydrogen bond between water and carbonyl oxygen. As a result, the energy of an electron to carbonyl oxygen in ground state decrease by an amount equal to the strength of the hydrogen bond. Consequently, the N2 pi star transition of carbonyl compound require more energy and therefore it is shifted to lower wavelength. For example, N to pi star transition of acetone in hexane non-polar solvent take place at 279 nanometer, but in water protic solvent it occurs at 264 nanometer. For the above hypersochromic shift of 15 nanometer, the strength of hydrogen bond between water and acetone can be calculated. Study of ketoenol tautomerism. In case of compounds which exhibit ketoenol tautomerism, UV spectra show characteristic absorption band of both the keto and enol forms. For example, ethyl acetoacetate, which exists as an equilibrium mixture of keto and enol tautomers, shows two absorption band for keto and enol form respectively. The keto form has lambda max is equal to 275 nanometer with very low intensity, while the enol has form delta lambda max is equal to 244 nanometer with very high intensity. Quantitative analysis. UV spectroscopy provide a very sensitive method of quantitative analysis. It is based upon Beer-Lambert's law, which relates the absorbance of a substance with its concentration, path length, and molar absorptivity, that is A is equal to ECl. For example, we can find the concentration of vitamin A in a sample by determining it.